In this video, I want to talk a little bit about arithmetic. Arithmetic is something that you do all the time. You do calculations and determine the value of stuff using operators on operands. That is basically what we're talking about. You cannot say arithmetic without variables. Of course, you can do arithmetic on constants, but the output will always be constant, and the fun of programming is in the fact that you have variables. So we're going to do a lot of operations on variables. So I thought it would be smart to actually have a short look again at what we've talked about in previous videos about types and variables. A type defines a set of possible values and a set of operations for an object. So we've talked about how each variable must have a type. Take an integer. The integer type defines the set of values that the variable can have. But it also defines the fact that you have a plus and a minus and a divide and all those. Now just keep that in mind when we make our own types, that we can also set the operators for them. An object is some memory that holds a value of some type. That's how easy it is. A value is a set of bits that's interpreted according to a type. Now that's slightly technical, but any value, whether it's a very simple one or a very complex one, they're all just a series of bits. And it's the type that actually defines how the computer will interpret the data that is there. And a variable is simply just a named object. And another thing that we've been talking about is program structure. So very briefly, I'll recap that. So we start our program with some declarations, and we can write our own, or we can include them from a library that we're going to use. So if we're using the IOStream library, we type this. We always do that at the top of the program, and this will import a number of declarations. Then the next area will have the definitions. Now the difference between a declaration and a definition is that we can declare a function or we can declare a class, and that will just give the user the names of the functions and the parameters that they'll use. But they won't say how the function actually works, because that is what you do in the definitions. We'll get back to that when we talk about functions, but the definition section is after the include and before we actually begin our own program with int main. So the basic structure of our program is declarations, then definitions, which we have none in this program, and then the definition of our own main program. Now applying operations is something that is intuitively easy to understand. Let's have a look at the whiteboard, what I mean. If I add two numbers, like I can add 1 and 2, it makes a lot of sense that this is an integer and this is an integer, and plus is the addition operator. So we apply the operation plus to 1 and 2. And we know what plus means because these are just two integers, and plus means addition. And the plus can be minus, it can be a divide, it can be any of a number of operations. If we generalize this, and we say x, and we'll take an operation, we'll take plus, and y, then these two, and I'll link them together as best as I can, are called the operands. and this guy in the middle is the operation. Now, if we generalize this, then this x, which we saw was an int before, and that's usually how we imagine operations, but this x can be any type that we define. It can be a very complex player structure or a class of some kind, a matrix, 3D matrix. And that has something to say about how this operation is supposed to work. And what is supposed to happen if this variable is of a different type than that variable? How do I add a 3D matrix to an integer or a float? What is supposed to happen? What should be the precision of an addition of two integers or a division of two integers? That is all defined by what the plus operation does. Now, in C++, we already know that we can define our own types, the user-defined types, but that also implies the definition of what the operations do. Now, here's something that is easy to forget, but C++ does whatever meaningful conversion between the basic types that makes sense in the operation. So an int to an int or a float to a float. When it comes down to the basic types like the int, the character, the float, and the double, C++ does that automatically. Now, and I'm going to read this from a note that I have here. The conversions used in expressions, and they're called the usual arithmetic conversions, aim to ensure that expressions are computed at the highest precision of their operands. Now, that sounds a bit formal, but what it means that if you have two integers that you add together, the highest precision of those integers is just, an integer is a whole number. So that will be, the highest precision will be that of an int. So the result of the operation will be an int. Also, if the operation is division. Now, to make that clear, if you divide 5 by 2, you get 2.5. But in C++, if you have two integers and you divide them, the result will be an integer because the highest precision of those two variables was that of the integer. Now, let me demonstrate that in a tiny program. Okay, so here's our little program. I'm going to declare x and y as both integers. And I'm going to initialize them in the way that we spoke of before. Right? This is an alternative way of initializing your variables. It makes sure that there's no problems in narrowing conversions. Now, if I use this cout and I would say x over y, so 5 over 2, and then an endl, and at the end we return a 0 because our function should return an integer, so we're returning 0. We immediately see that there's a small problem because cout isn't a known thing, neither is endl. Now, these come from IOStream, but they are in the std namespace. We've talked about namespaces before, so what I could do is type this std cout and std endl so that we know that we're taking the right functions. Now, I'm going to press F5 to run this program, and if you expect to see 2.5, you're going to be wrong. So here goes, F5. Now, there's some extra output here. All this text, you can ignore that. But look at the tiny little 2 at the top here. That's not 2.5. That's 2. This is exactly what is meant by the highest precision of both operands. The highest precision of both of these operands is that of an integer. Now, if we took the y and turned that into a float y2, now the highest precision is that of the float. So if I press F5 now, you can see the output again, but now, look at this, now it's 2.5. Why? Because the highest precision of the operands is that of float, and the output will be the precision of a float. So let's have a look at the most basic operations that you can do. So we've seen the divide by. Let's change this around a little. We'll make a float. We'll call it result. And we'll say result equals x plus y is 1. X minus y, of course. We've seen x divided by y. There's also result modulo. Modulo means the remainder after division. So in this case, we divide x by 2, and whatever remains is put in the result. Other operations are, of course, minus x, which will give us the negative value, but also plus x. This is also possible. Now, what will often happen is that we want to add a constant value or whatever. So we say result is result plus x. Now this happens so often, and it just results in a pretty long expression with one of the variables being named twice. So what they did is they added this, the plus equals x. This means the same thing. So result plus is x means result is result plus x. And they exist for all of them. Minus equals x, result divides equals x. Result, we forgot multiplication, of course. X. I'll add that here as well. Result equals x times y. Almost forgot. Now for modulo, we need an int result, which is a result but as an integer. So int result modulo equals 2 also exists. Now there's another special case for operations. For this one, if we want to do this result equals result plus 1, we could write result plus equals 1, but some people still felt that this was too long, so they added result plus plus. Now, these are clear enough. Again, you tend to think in terms of integers. And in that case, it makes sense. If result was some strange matrix or some other user-defined type, plus 1, what does that mean? Right? It's not always clear. If you do plus plus, it's the same thing. It doesn't even mention a type. The 1 here is an integer in itself, but the result plus plus, if result is of type weird game character or some mathematical construct, what does it mean? Right? You have to define it, and you can. But this will add 1 of whatever type result is. Now there is another side effect of this operation, because there's another form of this, which is plus plus result. Now, you may think, what the hell is the difference? I'm going to type a little example here. If I have an int u, suppose, and I have an int z, And if I said, well, u equals 5, and I said z equals u plus plus, oops, and then I said C out z, and of course I have to add the standard. The result of this might not be what you expect, because the result will be 5. Let's have a look at the output. See, forget about this extra output here. The result is 5. Why is that? Because I said plus plus, right? Well, because the plus plus is placed behind the u, it means that z gets the value of u before it was increased. After the assignment, u will be increased. Yeah. If I wanted it to be 6, I typed this, then z would get the result of this before. Right? If I did this, ran it like this, now I get 6. See here? 6. So the placement of this operator in front of or behind the variable that you want to increase, it makes a big difference. And you have to be wary of that. Naturally, this also comes in its minus form, so is minus minus u, or z is u minus minus, with the same rules. Now, you can't do programming really without doing some kind of comparison. So there are also comparison operators, which will compare two values and yield the result of that. So let's just first create another example. We'll say u equals 5 again, z equals 5 as well. And if I said x equals y, then that would compare x and y. So this looks like the assign up here, but because it's two equals symbols, it's a comparison. It's not the same. This does not mean the same as x equals y, because this is an assignment and this is a comparison. There's a big difference. I can also test if x is unequal to y. So if I say x is not y, then that is a valid test. So it's an exclamation point and an equal sign. Means unequal. We'll see this exclamation point used in the same kind of role again. Naturally, I can check whether x is smaller than y or x is larger than y. Well, this is all basically pretty simple. You can also test if x is smaller or equal to y, x is larger or equal to y. So these are all the basic operations, and they yield a Boolean value of true or false. Because in each of these comparisons, they are either true or false. So x is either equal to y or it's not. So, and the fact that this yields a Boolean value of true and false means that we can take decisions in our program. If x is equal to y, then do this. So this is used in, well, probably the most used operation in programming is testing whether values are equal or different or lower or higher. Now for this next section of the video, I am going to talk about bitwise operators. And to do that, I have to talk a little bit about the binary representation of numbers. Now, I don't want to spend a whole lot of time explaining the binary system, but I do want to make a small effort to at least get you going. If you don't know how to work with binary or what it is, then you are likely to not use the bitwise operators. But I still think, it's important enough to spend some time on it. So make a new little program, and I don't want to be typing the std namespace all the time, so I'm going to say using std cout and using std endl. So now I can just name them without using the std all the time. Now, okay, I'm just going to use the editor as a little bit of a canvas. Our usual numbering system is based on the number 10. So what that means, if I have a number 234, for instance, what does that mean? Well, it's 4 times 1, and it's 3 times 10, and it's 2 times 100. If you add all these up, you get 234. So each position is worth a factor of 10 extra. See, this is worth 1, this is worth 10, and this is worth 100. Now these numbers that I have here, they are actually the same as 10 to the power of 0. This is 10 to the power of 1, and this is 10 to the power of 2. And this goes on. If it were 1200, then this would be 1000, and this would be 10 to the power of 3. So the fact that each digit in this numbering system can have 10 different values has something to do with this 10. Yeah? So this can have a digit of 0 to 9, which is 10 different ones. So each next position is worth 10 more, right? And this is a factor of 10 more than the last one, and so on. So, but we're not limited to 10. We could do anything. So if I wanted to make a numbering system where each position could have only 2 values, like a 0 or a 1 and no more, I could write something like this. Now this is a binary representation of a number. So it's 1 times 1, which is 2 to the power of 0. Now I write 2 instead of 10. 0 times 2, which is 2 to the power of 1. And then 0 times 4. Why? Well, that's 2 to the power of 2, of course. And that's 1 times, let's just do 2 to the power of 3. Yeah? Which is 8. I've turned them around now. 1 times 2 to the power of 4, which is 16. And then 0 times 2 to the power of 5, which is 32. 0 times 2 to the power of 6, which is 64. And then finally 1 times 2 to the power of 7, which is 128. So any number can be represented in a binary form. It'll give us more digits because we can have only 2 per position, so it's less powerful maybe, but it'll be equal to the same number in decimal or maybe hexadecimal. We came up with hexadecimal so that each position can have 16 different values instead of just 10, right? And there's octal, and there's a you could make up anything you like. The reason we chose binary, of course, is that inside computers, in logic circuitry, you can have either a 0 or a 1. So it makes sense to have a binary representation of numbers. So anytime a memory location, which can be a register or it can be something you read, it'll have a value that can be represented in binary form, zeros and ones. And sometimes you want just one of those bits. You want to test what is the value of that bit. Well, that is where the bitwise operators come into play. I'm going to make a little comment space here so they can type whatever I want. Suppose we have two values, x and y. There are some logical operators that are specifically meant for binary values. And they'll make sense as I explain them. And I write them this way. So x and y. This is the ampersand. It's a logical choice. X and y tests whether x and y are both true or not. So, being binary values, I can simply make a table that lists all of the possible combinations. So, if both x and y are 0, I'll just make the complete table. X is 0 and y is 1. X can be 1 and y can be 0, or they can both be 1. We can also call them false and true. So, these are all the possible value combinations of two binary values. Now, if both x and y are 0 or false, then x and y are obviously false. The result of the operation of 0 or false and false, well, it's false. They're both the same, but the result is false because none of it's true. In this case, if x is false and y is true, then what would be the result of x and y? Are they both true? No. So the result is false. The same here. The values are reversed. The only case where x and y turns out to be true is this one, if x and y are true. There's another operation, and I'll make a new table. I'll just copy the old one because it'll be easier. And the new operation will be not and, but it will be, it'll be or. And that's the pipe symbol. Now the results here are different. This tests whether either x or y is true. Well, in this case, if they're both false, then nothing is true. In x or y, in this case, y is true, so the result of this will be true. Same here, same here. In this case, they are both true. So if x or y have to be true for this to be true, then, well, it's true in either case, yeah? Now, there's a last operation, and I'll remove these again. And the last operation is the exclusive OR, which is the correct symbol. Or is that correct? I don't know. It's that one. This is called the exclusive OR. I'll write them above the tables. This is AND. This is OR. And this is exclusive OR, or XOR. Now, this tests whether either X or Y are true, but not both. So, you can predict the results maybe. Is X or Y true? No, neither. X or Y, yes, Y is true and not X. X or Y, yes, X. In this case, the exclusive OR, because either one exclusively has to be true, so when they're both true, the result of this is false. So these are three very basic logic tables and their logic operations. These are bitwise operators. Now, you may be wondering why I'm telling you this and why this is important. It may not be important until you run into it, and then it will be important. So just take it as a reference. But I'll give you a small example. So let's look at a tiny program. Let's say I have two values, and let's say the value here, which is 234, which we saw before. Let's say we read that from some device that we have connected to our computer, right? It can be a joystick, it can be a paddle, it can be... Suppose that would be like the up on a joystick, right? If we push our joystick up, then a register in our computer will have this value, and this bit specifically that I'm marking here, it will be 1 if we're pushing up. So we have to test whether that bit is set, yes or no, in order to make our player character go up. Now, this is a real-life example because this happens a lot, especially on 8-bit computers. But just using a single bit for an operation that can be either true or not is very common. So I've written the numbers out in their binary form here. So in order to test whether or not this bit is set in this number, what I can do is I can perform an AND operation on both of these. Because if I do an AND and I make all of these 0, then I'm going to be sure that the result of that will be 0, whatever it says here, and also on this side. So if I just leave the 1 in there, then I'm going to have the result depend on this bit, which is exactly what I want. So I'm going to make a Boolean, which has a bool type. It's going to be result, or I can call it up pressed for some, reason. So up pressed is X, bitwise and Y. So what this will do is exactly what I said. It will do a bitwise AND on all of the bits of this number. And depending on the value of this, the result will be either true or it will be false. The result will be whatever this bit is. So I'm going to introduce something, and it's called the if. So if up pressed equals true, so we're also doing a comparison now. Cout up pressed and an end line. Oh. So there we go. We've written an actual program. We do a check. We say if, and between these parentheses, we do whatever the check must be. It can be as complex as we can think of, but in this case, we just check whether up pressed is true after this operation. If it is true, then it will execute the command between these brackets, which is just to print out up pressed. So let's see what happens. I press a 5, and it says up pressed. Why? Well, because this bit is true. Now, if I quickly subtract 32 from this, and this will be 0, that will be 2, and that will be now 0. If I'm not mistaken, if I press F5, now it should not say up pressed, which is exactly the case. We do get the spurious output though, but there's no text there. We could also say, well, if up pressed equals false, then cout up not pressed end L. If we run it now, we should see up not pressed. And see, that's exactly what we get, up not pressed. So if we come to a decision where we have to check whether a single bit in a number is set or not, then we can use these values. We can also use the OR, which tests exactly the opposite. So the logic changes, of course, but we can do OR, X or Y. We also have the complement is what they call this, the unary complement. Officially, what that does, it flips all the bits around. So whatever is a 0 becomes a 1, and whatever is a 1 becomes a 0. I won't go into when that is useful, but just know that it exists. The binary operators, they may be quite a lot to take in, but they are going to be important somewhere in your programming career, I am sure. You'll recognize that moment when you think, this is where I can use them. And I've had that recently in a case where we were testing license keys, and I was meant to check whether or not a certain bit was set to recognize whether or not I had the right key. And lo and behold, this was the most efficient and shortest way to test whether that was the correct bit set, yes or no. So it's going to come in handy, especially when you're going to do 8-bit programming. These are not to be confused with their Boolean Logic comparisons and tests, because they are the next thing that I'm going to be talking about, and also the last thing in this video. So let's have a look. So suppose we have two Booleans, and one is up pressed, and we're going to set that to false. And we have another, which is fire pressed, and we're also going to set that to false. Now, instead of testing for single bits, I can also test for false and true, but because the false and trues I cannot use in a bitwise test, because false will be 0, a true will be something not 0, so no bits, right? So what I can do is this: if up pressed and fire pressed, then do whatever, jump and fire. Right? So I use the same ampersand, but in this combination of this double ampersand means that I do a comparison of two Booleans, and I just test whether or not they are both true, yes or no. Right? So there's also its OR equivalent, which is basically the same, but it's two pipe symbols. If up pressed or fire pressed, then jump. In some systems, up is jump and fire is jump. Now, as I said before, any comparison yields a Boolean true or false. So again, if we have int x equaling 5 and y equaling 5, I can also say if x equals 5 and y equals 5, then both x and y are 5. Right, so in this case, the x equals 5, and I'll put them in parentheses just to make it extra clear, that the x equals 5 yields a true or a false, depending on whatever the situation is. Yeah? So, I could have written bool x is 5 equals x equals 5. Right? And again, just to prevent the confusion, I'll put in some extra parentheses, but this result, x is 5, is the result of this comparison. X equals 5? Yes or no? Well, whatever is the result of that, that goes into x is 5. And then I could have said, well, x is 5. And the same goes for y. But it's easier just to put the entire comparison in here sometimes because it's short. Sometimes this can be a very long expression. What I've marked here can be very long. So then it might be a good idea to have a Boolean variable that does the test, and in the if statement you just write down the shorthand result of the test that you did before. So these ands and ors are very important. Also note that we, let's just continue in this, x is not 5 equals x is not 5. Right? So this comparison we saw earlier, right? X is not 5. It's a question, yes or no, true or false. Well, whatever the result of that is goes into x is not 5. So x is not 5 is the name of a variable which is very specific. X is not 5, and that is the test that it does. X is not 5. And with these, well, once you realize that every comparison that you do yields a Boolean value of yes or no, true or false, then you get to understand why these logic operators are necessary and important. You will use them all the time. What we could have also done, because x is not 5 and x is 5 is, well, they are mutually exclusive. So I could have written this. Now here goes. Okay. So by adding the exclamation point in front of this Boolean value, I reverse its meaning. So what? Here goes. So x equals 5? Yes or no? True or false? Yes? Okay. X is 5 is that value. X is not 5 is not x is 5. That makes sense, doesn't it? So suppose if x was 5, as it is now, then x equals 5, question, x equals 5? Yes, so the answer will be true. So x is 5 will be true. X is 5 is true. Not x is 5 will be not true, which is false. So x is not 5 will be false. Get it? So these are powerful tools. They're very simple Boolean logic tools, and, or, and not. And in digital thinking and wherever Boolean logic rules, then these are the operations that you need. And any comparison that you do will result in trues and falses, and you'll have to test for them. That is the end of my operator and arithmetic talk, basically. It may have been confusing. If you've seen it for the first time, your head may be spinning right now, but just go back in the video and watch it again. If you have a question, just ask. This is very basic stuff in the sense that it is the foundation of programming. Trues and falses. Computers are all about yes and no, 0 and 1, true and false. So getting to know these operators, knowing about types, and knowing about the operators that are defined for them is very important. So it's very valuable knowledge to have, and something that you have to be able to just splurt out at the moment that you need it, because if you're doing programming, then this is your bread and butter. This is really the foundation, as I said. So I hope you enjoyed it. Thanks for watching, and I'll see you next time. Bye-bye.